Every heavy-duty storage trunk starts as a vulnerable sheet of raw steel. The first step is isolating the exact dimensions needed before the metal resists shaping. Using a wooden mallet rather than a steel hammer prevents surface marring. The initial edge folds establish the structural geometry, stiffening the flat panel against twisting forces. The hardware serves dual purposes. Embossed plates distribute the stress of the fasteners over a wider surface area. Without them, a heavy load could tear the rivet heads straight through the thin gauge steel. Hundreds of these manual connections will eventually bind the loose geometry into a rigid, load-bearing shell. The craftsman secures each one by hand, seating the rivets precisely to ensure weather-tight compression. Returning to the main body panels, dimensioning is critical. Even a millimeter of variance during the primary shearing phase will compound into massive misalignment once the walls are erected. Hand shears demand immense grip strength, slicing through the zinc-coated alloy millimeter by millimeter. Transforming two-dimensional sheets into three-dimensional structure requires brute force and controlled leverage. By trapping the steel over an anvil rail, the craftsman forces a hard crease. Galvanized steel carries an invisible zinc coating that protects against rust. Bending the metal too sharply with improper tools could crack that protective layer, inviting corrosion down the line. The heavy wooden mallets deliver broad, blunt trauma. This forces the rigid alloy to yield and hold its new shape without fracturing that defensive outer skin. As the scale of the panels increases, the resistance of the metal multiplies. The work becomes a highly synchronized effort. While one worker sets the alignment and applies downward pressure, the other drives the fold home. This coordination prevents the long steel sheets from springing back and bowing in the center. Metal memory is persistent. It constantly wants to return to a flat plane. Overcoming that structural memory requires driving the crease slightly past the target 90-degree angle. They anticipate the subtle, inevitable springback when the physical pressure is finally released. The resulting hem is commonly known as a safety edge. Folding the raw, sheared steel back onto itself completely eliminates the razor-sharp burrs left by the cutting process. Crucially, it also doubles the material thickness at the perimeter. This drastically increases the torsional rigidity of the final panel. A clean, perfectly linear crease is the true hallmark of manual metalworking. Any waves, dimples, or deformities in this folded edge would create widening gaps during the final assembly, entirely compromising the trunk's ability to keep out dust and moisture. The relentless, percussive hammering pays off in severe geometric perfection. Moving down the production line, the pre-folded components are prepared for final joining. The craftsmen rely on a massive inventory of soft metal rivets to bridge the gaps. Unlike screws or bolts, which can vibrate loose over time, a properly set rivet expands inside the hole. It forms a permanent, mechanical lock that fuses the independent steel sheets together. The ornate floral heads are traditional, providing both structural grip and a signature aesthetic touch. Setting the rivets requires precise seating before the final hammer strike. The metal shank must pass completely through all overlapping layers of steel before the head is crushed flat. They install heavy-duty handles on the side panels, anchoring them through reinforced backing strips. Lifting a fully loaded storage trunk places massive shear stress on these specific focal points. Without adequate backing to distribute that weight, the handles would eventually tear right through the thin-gauge sidewalls. Working as a tandem, the team settles into a percussive rhythm. One craftsman aligns and seats the hardware while the other drives it home. The flat, featureless sheets are rapidly gaining the heavy-duty hardware that will define their ultimate function. Every hammer strike creates a localized compression ring in the steel, tightly sealing the metal joints against moisture intrusion. Moving on to the main body, the flat walls face a critical vulnerability: oil canning. A large expanse of thin sheet metal will flex and pop under pressure. To counteract this, they press deep horizontal ridges into the broad panels. This technique, known as swaging, introduces artificial topography to the metal. By stretching the steel into these long channels, it gains immense lateral strength. It is the same structural principle used in shipping containers and automotive floor pans. A flat wall is weak. A corrugated wall can bear massive weight. The newly swaged panels are immediately much stiffer, ready to form the core chassis of the trunk. Inside the trunk, organization requires internal framing. They lock a central divider into place, capturing the raw edges in a folded seam. This inner tray does more than just separate contents. It acts as an internal brace, pulling the opposing walls together, and preventing the long sides of the trunk from bowing outward when packed full. The geometric network of dividers essentially locks the outer frame into a rigid, untwisting box. The top rim receives a heavy hand-folded lip, creating a blunt, reinforced collar around the entire opening. This rim will eventually seat the lid, so its perimeter must remain perfectly square. Even a slight twist here would cause the final top to wobble and bind. They carefully attach the locking hasps, driving the rivets flush. Finally, the sub-assemblies are brought together. The reinforced side walls are married to the base structure. The sequence of assembly is critical. Joining the wrong corners first would block hammer access to the internal seams, making it impossible to crush the final locking folds. With the main sections interlocked, it takes tremendous physical force to set the final structural seams. The heavy wooden mallets drive the standing corner joints tight. These interlocking folds operate much like a mechanical dovetail joint, actually gripping tighter as more compressive force is applied. Beating the seams completely flat permanently locks the independent steel walls into a single, cohesive shell. The sound in the workshop changes as the structure solidifies. The tinny, hollow rattle of loose sheet metal is gradually replaced by the deep, resonant thud of a unified, rigid chassis. A final inspection ensures the chassis sits dead level. Any residual warping is beaten out with precise, targeted strikes. The main body is complete, heavily armored, and structurally sound. The upper lip is hammered perfectly flush to receive the overlapping lid. Securing the main front latch plates requires dead reckoning alignment. If they are mounted even a fraction of an inch too high or low, the tensioned locking mechanism will either rattle loosely on the road or stubbornly refuse to snap shut. The heavy top lid is married to the rear hinges. The overlapping flange acts as a rain gutter, designed to deflect water away from the interior lip. Once the hinge pins are fully seated, the geometry is locked. What began as a flimsy, two-dimensional sheet of raw alloy is now a fortress of folded steel. Through thousands of calculated hammer strikes, raw material has been transformed into enduring utility. The structural integrity comes not from the thickness of the metal, but from the intelligence of the folds. It is built to carry weight, take a beating, and survive the long haul.